All right. Go ahead and put everything away except for a pencil. You won't need a calculator. Let's do practice exercise 59 as we get started today. Practice exercise number 59, continuing our review of algebra concepts here. Exercise 59, you won't need a calculator. Practicing with some signed number operations, more of a review here with some addition, some subtraction, multiplication, division, and just a few equations for you to solve as well. Exercise 59, you may begin. As we did yesterday, first one to finish, please stand and keep track. Did you do the bottom part? Yeah. Sit. I'm supposed to win, it's not you. But if you can't talk, go ahead. I just don't want you guys to know what I'm talking. No, I'm sorry. Put your pencils away if you would, please, and take out a pen. Pencils away and take out a pen. If you're doing exchange, since you do not have your own, exchange with the person behind you, first the back, you can pass it up to the front. And in pen, sign your name next to where it says exercise 60, there at the bottom of exercise 59. Sign your name next to where it says exercise 60. They're at the bottom of exercise 59. There's going to be 6 points each. 6 points each. Going across the top row, your answers: -2, positive 36, or of course just 36, positive 2, -6. Next row, -3, positive 60, positive 19, -13. Next row, 0, put a sad face if they missed that, -4, -16, 17, or positive 17. And the bottom row, solving those equations, your answers should have been 9, 6, 6, and 10. Again, 6 points each, figure the total number incorrect, and multiply that by 6, subtract from 100. Question, Chris?
The -5 plus -6 plus -7. What was the answer for that one again?
The
second
last
row.
one, second row?
Yeah.
-13.
Okay.
Ethan, question?
Can you repeat that? Can you repeat the second row up top?
The whole second row?
Yes, sir.
Oh, man.
I got messed up.
All right, -3, positive 60, positive 19, -13. All right. 6, yes, ma'am.
Where were we supposed to put the grade?
Right next to where it says exercise 59. So once you figure the score at 6 points each, figure the score, put it next to where it says exercise 59, and then return it to the owner. Quentin, you were first. Did you get 100? You did. Excellent job. Anyone else get 100, though maybe not as fast as Quentin? Good. Several hundreds. We get another one there. Saw a couple of people exchanging late. All right. Okay. Any 94s? Just missed one. How about an 80-something? Just missed 2 or 3 of them. All right. Questions on any of the ones we missed? Any of these say, can you explain how I should have done that? I'm confused.
I forgot that you had to change the sign, like -12 times -3.
Okay, so remembering that an even number of negative factors gives you that positive product. Okay. Yeah, I think that goes back to exercise 54 was when we reviewed that. So it was several exercises ago. All right, any other questions, comments? All right, go and pass those forward if you would, please. And take out your homework. Books open to page 156. Pass them forward and homework out. Books open to page 156. You did page 156, number 4 for homework last night. And while you're getting out, let's go and quickly review some things we talked about in our last lesson. We've been working on arcs and angles and all kinds of different angles with respect to all different kinds of arcs and stuff. And of course, class, we said an angle formed by a chord and a tangent is equal to half its arc. An angle formed by 2 secants outside a circle.
Equal to half the difference.
Half the difference of the 2 arcs. An angle formed by 2 radii.
Central equal to the
equals the arc because it's a central angle. Good. An angle formed by a secant and a tangent outside a circle.
half the sum.
Half the sum, or half the difference of the 2 arcs. It's outside the circle, secant, tangent, half the difference of the arcs. That last case we talked about. If we said we had an angle formed by 2 tangents outside a circle.
Half the difference.
Half the difference. Same as secant and tangent, same as 2 secants. An angle formed by 2 chords intersecting inside a circle.
Half the arc. Half the sum.
Half the sum of the 2 arcs. Angle formed by 2 chords intersecting on the circle.
Half the arc.
Half the arc because it's an inscribed angle. But then yesterday we deviated from that just a little bit, and we proved that if you were to get 2 parallel lines to cut a circle, what must be true, Kendall?
Arcs in between are equal.
Good. The arcs cut off in between them must be equal to each other. Building on that thought, then, we said that if you inscribe any trapezoid in a circle, Jamie, it must be
Isosceles.
Isosceles. We also showed that if you were to inscribe any parallelogram in a circle, Ethan, it must be a rectangle. So several things from yesterday to recall. Go and hold up your homework if you would, please, so that I can see that it is completed. Leave it up till I tell you to put it down.
I got stuff.
Oh, interesting approach on that one. All right, most of you had a pretty solid approach to this. Let's take a look, see how we did. Given a pretty benign given here, and that was simply we had a couple of equal chords. So there was the center of our circle, O. We had a chord going up here, A, B, and then we had an equal chord. So that same length, that same distance maybe from the circle or something like this. That's not drawn very equally looking. Whatever, we don't trust our eyes. CD, and they intersect at point P. All right, so whether we trust our eyes or not, so what? We're given that AB does equal, contrary to appearances, CD, and we're being asked to prove that if two equal chords intersect in a circle, that the pieces of the chords have to be equal. Now again, it doesn't really look that equal in the picture, but we're going to prove that regardless of how it appears, that AP and CP have to be equal, and that BP and DP have to be equal. So if equal chords intersect in a circle, the segments of those equal chords must be equal to each other as well. All right. Now I will say there is a little bit of clang here. What's the clang, Ethan? Genesis, help them. What's the clang from the given?
Equal chords.
Equal chords. What's the clang to equal chords, Genesis? I'm sorry? Not necessarily. Been around since we first started talking about circles. Equal chords, class? Equal arcs, right? So if AB and CD, the chords are equal, then Genesis, back to you.
BC, arc, BC.
What is the arc of AB? Don't overthink this. What's the arc of AB? AB. What's the arc of CD? CD. Right? CD cuts off CD and AB cuts off AB, right? So if AB and CD, the chords are equal, then AB and CD, the arcs are equal as well, because, back to Ethan,
If equal,
let's start with in a circle.
In a circle, if chords are equal, then the arcs.
Ooh, if chords are equal, then the arcs subtended are equal. Okay, by them are equal, or the arcs they subtend are equal, something like that. So that tells me that this arc and that arc are equal to each other. That's really about the only clang we've got, frankly. Equal chords, equal arcs. Okay, let's look at what we're trying to prove. I'm trying to prove that this line and this line are equal, and that that line and that line are equal. I want to get some equal line segments. Chris, how might I get a couple of equal lines?
Well, I don't know. The way I thought about it is if I draw AO and CO, if the chords are equal, I said in the same circle, two chords are equal, then they're equal distant from the circle.
Ooh, would AO be a distance from O?
Why wouldn't it be?
Oh, Audrey, how is distance defined? From a point to a line? No. The perpendicular, thank you, Genesis, saving the class. No, the perpendicular would be the distance, not necessarily AO would be a distance. It would be a radius, but it wouldn't be a distance of the chord here.
So I could use that, because I tried to get equal radii.
I mean, you could get equal radii. I don't know that it actually would help us to get equal radii.
That's probably what I got stuck.
Yeah, I was struggling quite.
Equal angles? It'd just be
So if I want these two lines equal, and I want these two lines
We
equal,
can get their arcs equal, right?
they're arcs?
I mean,
AP has an arc?
no.
AP doesn't have
Wait,
an arc.
chords
does
the
it?
same distance from the center. Distance again, the same thing.
Right, we'd have to get perpendiculars. That could get, I mean, it might work, but it probably gets kind of dicey.
I'm looking at this, it says two lines are equal if they chords of equal central angles, or equal arcs. Chords the same distance from the center, tangents from the center.
But I'm not trying to get chords equal. I'm trying to get pieces of chords equal. I'm trying to show that just because two chords are equal, if they intersect, they have to cut off equal pieces of each other.
Draw AC.
And that's not something we've necessarily seen before.
Do we draw one?
What about draw AC?
Drawing AC? Okay, now there's an interesting thought here. Let's entertain this thought for a minute. Do we all see that if we were to draw this chord AC, it forms what shape class? A triangle.
Also makes an inscribed.
And if it's it's not inscribed because the vertex isn't on the circle, but it does make a triangle. And if it makes a triangle and we want two sides equal, I would need to get, call this angle 1, this angle 2. I think that might be a viable option, right? If I can get these two angles equal, then these two segments would have to be equal. I think that might work, yes, sir.
So ACD, that angle is not inscribed.
Oh, okay, I'm sorry, angle ACD. I thought you said the triangle was inscribed, because we just said a triangle, and then you said it's inscribed. No, the triangle's not, but the angle certainly is. This angle we call 2.
So if we get, no, that wouldn't work either, because we don't know that AD and BC are equal.
Okay, so do you see the pattern that he's saying? He's saying, well, what if we just got this arc AD and this arc BC equal?
With their parts of
Well, if they were equal, this inscribed angle is equal to half the arc. This inscribed angle is equal to half of that arc. This is not the way I did it, by the way, but this will work. If I could get these pieces of arcs equal, which they don't look equal, but my drawing's pretty horrible, let's face it. If these two pieces of arcs were equal, these little arcs, then the opposite angles, which are halves of equals, would have to be equal. And if the angles are equal, then the segments are equal. Right? Can we get AD and BC equal? All right. Quentin says yes. He said it very confidently. Now, did you actually do this in your proof by any chance?
No, I didn't.
No. But you're pretty confident you could get AD and BC equal. Okay, Quentin, do tell. What are your thoughts?
Arc AD equals arc AD plus BD. And
Okay, so hold on. Let me say it for the camera so you can hear as well. This whole arc is equal to the sum of its two parts.
And arc CD is equal to arc CD and BD.
All right, so you're saying you're going to take this arc and the solid yellow arc and the dotted yellow arc, say each of them is equal to the sum of its parts, okay?
And then subtract arc BD.
Subtract away BD from both of them, and what that leaves you with is the two pieces left over. And BD, of course, the arc is going to be equal to itself. So yeah, let's take his suggestion here. This is not the only way to do it, but it's a great way to do it. And that's to say that the whole arc AB is equal to AD plus DB, because why again, class?
All those equal to
Similarly, Kendall, we could say that, I just said that AB equals AD plus BD. We could also say,
CD plus
because the whole equals the sum of its parts. And tying these two statements together was what Quentin was trying to do, Audrey. By substitution. And since there's a dB on both sides, Quentin, you said to simply subtract a dB from both sides, leaving us with
AD equals CB.
AD equals CB. So these two arcs here are equal to each other now by subtraction. And coming back to you, Chris, you said if those arcs were equal, then we could specify that angle. Oh, we don't have an angle 1 yet.
Make it.
because we haven't yet drawn AC, right? Not in the proof we haven't. We did it on the picture. I forgot to say it here. So number 6, let's draw AC, which was Chris's idea. Reason was,
2 points determine straight line.
hey Chris, you know what this means? This is the first time this year you suggested an auxiliary line and it's worked beautifully. Just throwing this out there. Okay, this is like all those moments of like, ugh, and now it's like, yes. Okay, so 2 points determine a straight line. Well played, sir. And so now we do have an angle 1 and an angle 2. And so we can say, Chris, that
Angle 1 equals half of arc BC.
and
Angle 2 equals half of arc AB. And then
because
inscribed angle equals half of its would it be corresponding arc?
intercepted arc, but I'm just going to be lazy and say inscribed angle equals half arc.
And then you could say halves of halves are equal. So
Halves of halves?
or halves are equal to halves of the same whole. I don't know how.
Halves of
Halves of
equals are equal. There we go. Halves of equals are equal. And if angle 1 equals angle 2, then class,
AP equals CP.
because Ethan,
Angles opposite, in a triangle, angles opposite equal sides. Well, angles opposite equal sides in a triangle are equal.
you said
Sides,
sides.
yeah, I said that.
Opposite equal angles are equal. In a triangle, sides opposite equal angles are equal. So that takes care of the first thing. All right, now BP and DP. There's an easy way and a hard way. And let's see, I haven't heard from Jamie.
So I can
I haven't heard from Genesis. I think I've heard from everybody else. Oh no, you did have over here. You did have this. So Jamie. It's just like, yes.
But if equals are subtracted from equals, then the remainder is equal.
All right, so your thought, Jamie, is to kind of like we did with the arcs, say that this whole chord equals the sum of its parts. This chord equals the sum of its parts. And since the chords were given equal, the sum of the parts would be equal. And if you subtracted the equals away, it'd leave you with equals. That's the hard way. There's a much easier way. But it would work. It would work. For the record, it would take us to like step 12 or 13, but it would work. Okay? There's an easier way though. Does anyone see it? Let me open the floor.
arc DB equals arc DB by identity.
Well, I mean, we could state that. It wouldn't necessarily help us here. Really easy way to finish it.
With the angles at, would that be DPA and BPA?
Well, yeah, of course these angles are going to be equal because they're vertical angles, but how about this? You know how we drew AC?
Draw DB and RB.
Let's draw BD. And let's call this angle, angle 3, and this angle, angle 4. Angle 3 and angle 4. What kind of angles are 3 and 4?
That's right.
They are inscribed, formed by chords. So we know that angle 3 in statement 7, let's squeeze it in there. Angle 3, because an inscribed angle equals half its arc class, equals half of
DB.
BC.
BC. Notice angle 3 cuts off BC.
Oh, yeah.
And angle 4 equals half of
Yeah.
AD.
They're already equal.
By the way, do you see that 2 and 4 must be equal? Do you see that 1 and 3 must be equal? Though I don't care about that, do I? I want to get, just as I got 1 and 2 equal, 3 and 4 equal. Because halves of equals are equal. And therefore, just as AP and CP are opposite equal angles, class,
BP and DP.
BP and DP are opposite equal angles as well. And it doesn't add a single step. It just adds twice as much stuff to each step we already had. That's the easy way. Your way certainly would have worked, Jamie. That is not the way I did it. All right, let me show you the way that I did it. And I saw some of you did this as well. Eraser.
Is it normally easier to solve proofs when you're like talking versus just looking at a piece of paper?
Well, when you are doing a proof, not out loud unless you're at home in your own bedroom or something, because nobody really wants to hear you talk, but, you know, it's fact, right? It's, any of you, not you specifically, but you, nobody really wants to hear you talking, like in study hall or at the kitchen table. Go to your room and lock it, but mentally at least, talking through the proof, asking yourself the same questions I would ask you, thinking, if Mr. Nadasky were here, what would he say? You know?
That's right.
Anyway, so we've got these intersecting chords here. And so what I did was I drew these auxiliary lines because after all, I wanted these two lines equal and these two lines equal, right?
Mm-hmm.
And those two lines are sides of triangles if I draw the auxiliary line. Now I already had these two angles equal because they're vertical. I got that pretty quickly. And I said, well, this angle 1 and this angle 2, both of them intercept BD. They're both halves of BD then as inscribed angles, therefore they're equal to each other. And then I said, well, I need to get some sides though, right? Because I could also do the same with these angles up there, but that's angle, angle, angle. That's similarity, that's not congruency. So I had to actually do the same thing with the whole arc equals the whole arc off the clang. The sum of the parts equals the sum of the parts. Subtract out this arc equals this arc. Therefore, this chord equals this chord. So by side, angle, angle, congruent triangles, both lines are equal by CPCTE. Though I think it took me, it was about 7 or 8 steps anyway, so it wasn't much faster to do it that way. But congruent triangles could have worked. Does anyone have another way you might have been able to do the proof? Chris, I thought you did it the first way.
Yeah, I'm thinking
question,
there's another way I think you do it.
Okay.
Maybe if you make it a trapezoid. Then,
how would you know it's a trapezoid? Because to be a trapezoid, it'd have to be parallel, right? Do you know they're parallel?
Yeah.
No. But it's, you know, it's a thought. It would happen to be parallel, though. Remember the picture we said this angle happened to equal this one?
yeah.
They would be parallel. So it would be a trapezoid. It would, in fact, be an isosceles
So at the
trapezoid.
point you figure that out, it's not really.
But yeah, by the time you get there, you've already got the proof anyway. So, yep. All right, any other questions, comments, thoughts? All right. You got your textbooks out. Open to page 157 now. Let's take a look at number 8. The discussion there. Number 8. This is a fun proof. I like this one. A lot going on in that picture. Before you try to copy the picture down, let's read what it says about the picture so we know exactly what it is that we are copying. And let's start by having Audrey read number 8 nice and loud for us.
Show some of the angles described in the segments of the circle, cut off five sides,
On page 157. Okay, 157, number 8 for us.
A, B, and C are chords of the circle O on opposite sides of center O. D and E are the midpoints of arcs, A, B, and C respectively. Prove that D, E cuts off equal distances in the chords A, L equals AK.
Read just the first sentence again for us, if you would, Kendall, nice and loud.
E, D, and MC are chords of circle O on opposite sides of center O.
I'm sorry, first 2 sentences, I missed that period.
D and E are the midpoints of arcs A, B, and AC respectively.
That's what we're copying down. So if you would, draw a circle, mark your center point O, as shown. Pick a random point, or better yet, let's not make it random. Let's pick it about where it is in the picture, a point called A. And notice from A, 2 chords are drawn. One chord goes really close to the center. It's called chord AB. The other chord is farther away from the center, AC. All right, do we see what we've got in the picture so far? And then it said in the second sentence that D and E are midpoints of these arcs. So we need to locate about the midpoint of AC, and we'll call that one E. And we need to locate the midpoint of AB, and call that one D. The last line we will draw joins those midpoints. The last thing we'll draw simply joins those midpoints. And you call the points of intersection on AB and AC K and L. Do y'all understand what we just drew in the picture now? Again, you try to just copy the picture down, you might not draw it quite right, but we have midpoints. That's significant, right? Clang should be going through our heads and we're not even ready for it. All right, so given circle O with chords AB and AC, technically on opposite sides of O, but I'm too lazy to write that. All right, D and E are midpoints of arc AB and arc AC, respectively. But again, I'm too lazy to write respectively. We want to prove that as we draw this midpoint connector, DE, that equal distances are cut off on the chords from A. That is, we want to prove that AL and AK are equal. Let's get that down. 2 columns, statements, reasons. Get down your first statement and your first reason.
Have we ever heard midpoints of a circle?
It's not a midpoint of a circle, it's a midpoint of an
on
arc.
an arc? Have we ever heard that?
We have. We've seen that before in at least one proof. We've used a midpoint of
I
an
feel
arc.
like there should be claims that, like, because midpoint
Is a point that divides
into 2 equal halves.
a segment, or in this case an arc, into 2 equal halves, right? So, Chris, I like the way you worded it too. You said 2 equal halves. So number 2, what might I state based on that claim, Chris?
D equals half.
Hmm?
No. Cuts into 2 equal halves.
D divides into 2 equal halves. D is not one of those halves. What are the halves?
Okay, AB equals AD plus
Okay.
BD.
I'm sorry?
AB equals AD plus BD.
Yeah, that's true, because the whole is equal to the sum of all its parts, but I thought you were going to do something with the midpoint, with equal halves. Genesis, can you help
AD
me?
equals DB.
Okay, there we go. Okay, arc AD equals arc BD. Genesis, back to you. Similarly, we could also state
Arc A.
he's going off the fact that D is a midpoint, therefore equal arcs.
Oh.
I would like you to go off the point that E is also a
Oh,
midpoint.
okay. AE equals or arc AE equals arc EC.
There we go. And the reason class.
Definition.
All right. Now, I also thought, Chris, you were going to say arc AD and arc BD are equal halves of arc AB. I don't know that we'll need it or not. We can always change it, change the wording if we need to here in a little bit. So I'm going to leave just a little bit of space here in case I need to reword it, because I don't know if I will or not, but I've already written it. I'm too lazy to change it now. Plus, if it works, I got off easy, because this is the easier way to write it.
Equal angles.
That's about all the Klein we've got, right?
We made more claim though.
We did?
Equal arcs means equal angles, right?
Well, equal arcs means equal central angles, or possibly, if you go about it using the half concept, equal inscribed angles. I don't really have inscribed angles. The only inscribed angle I have is right here at A, and I have no central angles. So,
Why wouldn't DKB equal AKB?
DKB,
Yeah, it's opposite equal.
AKE,
AKD.
AKD. Why wouldn't these two angles be equal?
Yes. If they're opposite equal arcs.
Oh, okay. An inscribed angle would be half its arc. An inscribed angle would be half its arc. Then there would be halves of equals. They would be equal, but this isn't an inscribed angle, so it's not half. What kind of angles are these, class?
I said equal. They're opposite equal arcs.
But there is no statement that says angles opposite equal arcs are equal. We never stated that. It's not true. Besides, it's pretty obvious. Just, again, I know we don't trust our eyes, but one very much looks obtuse. Yeah. One very much looks acute. I mean, I don't see any way they could be equal. But, class, what kind of angles are these? They're not central. They're not inscribed. They're just inside the circle, so half the sum. And that's the reason why, Chris, it doesn't work, because this angle is half the sum of its arc, which equals this one, and this great big one. This is equal to half of this arc and this little bitty one, right? So no, that's why they couldn't be equal here. All right, so again, as far as clang, that's it. Midpoint, clang, midpoint, clang. Let's switch to analytic.
Did we know AB is bigger than AC?
I'm sorry?
Do we know AB is a bigger chord than AC since it's closer to the center?
It appears to be closer, it appears to be greater. We have no reason to
Yeah,
believe it's
appears.
equal for sure, right? But there's no reason to believe it's equal, and that would be the only thing that could help us here. Let's turn our attention now for the third time to analytic. I'm trying to prove two lines are equal. What do we notice about these two lines, Ethan? Specifically, these two lines. There's lots of ways to prove lines equal, but these two lines happen to be
In the triangle.
in a triangle. So class, when I notice these two lines are in a triangle, my thought should be, Quentin, try to get a couple equal angles. Which angles equal specifically, Audrey? I'm assuming you mean these two, correct? 1 and 2, AKL and ALK. Do we all see that if I could get angle 1 and angle 2 equal, these two lines would have to be equal because sides opposite equal angles on a triangle are equal? Coming back to something that's going to sound very familiar based on what we were just talking about a minute ago, what kind of angle is angle 1, Genesis? Well, with respect to the triangle, it appears to be a base angle. What about with respect to the circle? It's just a random angle that's inside, right? And a random angle inside, that would be if it was on the circle. It's inside the circle. So it's not inscribed. Jamie, help her.
It's a vertical.
It's vertical to this one, but this angle is inside the circle. It's not a central angle because it's not at the center. It doesn't have a name. There's something I'm looking for, something we've done a lot recently, something I told you we used to do with numbers and we're done with numbers, but we're going to use them in proofs now. It's inside the circle. What do I know about that angle? Class, anyone? It's half the sum of its arcs. Its own arc and its vertical angle's arc, right? What are its arcs? Back to Genesis. DB and AE. Okay, what do I know about angle 2? Back to Jamie.
That is also equal to half the sum of its arcs.
It's also going to be half the sum of its arcs. What are its arcs?
AD and EC.
So 1 is going to be half of these two, and 2 is going to be half of these two. What do I know about these two compared to those two, class?
They're equal.
These are equal to those, specifically this and that. Yeah, so let's use the fact that angle 1 is equal to half of arc AE plus arc BD, as Genesis said. And let's use the fact that angle 2 is equal to half of AD and EC, as Jamie said, because an angle in a circle formed by intersecting, there's got to be a shorthand for that, chords, there's not, equals half the sum of its arc and its vert angles arc. I wish there were a shorter way to say that. An angle in a circle formed by intersecting chords equals half the sum of its arc and its vertical angles arc. Now you got to be careful here because you cannot say halves of equals are equal. Because although I know these are equal and these are equal, I don't know that the sums are equal yet. At least we haven't stated that the sums are equal yet. So maybe we should state that the sums are equal, right? We could state that, okay, AD and BD are equal. And if you were to add EC and AE equals to these equals, then the sums are equal. We call that the, if equals are added to equals, the sums are equal. We call that our addition axiom. And this is a statement that would be really easy to forget to state. But once we have it, 1 is half of that, 2 is half of that. So 1 and 2 are halves of equals. So therefore they are equal. Angle 1 equals angle 2 because not quite substitution, but halves of equals are equals. halves of equals are equal. Now, Jamie, you could do a substitution. You could then state number 5 that angle 2 is half of, and then plug this in its place, BD plus AE, by substitution, and then by substitution again, 1 equals 2. So 2 successive substitutions, but it's faster to say halves of equals are equal, right? And then, well, I got a little triangle here, ALK, and I've got 2 equal angles, 1 and 2, and if in a triangle 2 angles are equal, class,
they're equal.
Opposite sides are equal. So we can state that AL does in fact equal AK because sides opposite equal angles in a triangle are equal.
It's my favorite.
Kind of an interesting proof, right? Any 2 chords, so long as they're on opposite sides of the center, you plot their midpoints and connect them, you will always cut off an isosceles triangle. Kind of a neat proof. Questions on number 8. Questions on 8. All right. Let's drop down now to page 157, the 3.19b, that middle section. And number 1. Go ahead and read number 1 for us, if you would. Genesis, nice and loud. By the way, before you do that, I'm sorry. Do we see how we're continuing to use those concepts in proofs? Again, we can do it with math. We can use them in proofs, and we did that here even with the intersecting chords business. All right, go ahead and read number 1 there in exercise 3.19b, Genesis.
Prove that the angle between a tangent and a chord drawn from the point of tangency is equal to 1/2 the angle between the radii to the ends of the chord.
Read it for us again, if you would, Chris.
Prove that the angle between a tangent and a chord drawn from the point of tangency is equal to 1/2 the angle between the radii to the ends of the chord.
Quentin, one more time for us.
Prove that the angle between a tangent and a chord drawn from the point of tangency is equal to 1/2 the angle between the radii to the ends of the chord.
All right, so class, I need to start by drawing a circle, because it talks about tangents and chords and stuff. It didn't even say a circle, did it? Was the word circle even in there? No, but again, it was implied, right? So we start with a circle, and let's call it circle G to mix it up here. Circle G.
We need a chord and a tangent.
And we need a chord, and we need a tangent. And the chord is drawn from the point of tangency. So let's start with a tangent here. And let's see, I'm going to put a tangent right here. And I'll call the point of tangency T for tangent. And maybe we'll name the tangent M-E, me. All right. And there's a chord that goes from this point of tangency. We could draw it kind of across, or we could draw it kind of down. We could draw it really close to the center. We could draw it far away from the center. Jamie, what are you feeling here?
Away from the center.
Away from the center. Do you want to go kind of up or kind of down?
Down.
Okay, let's kind of go down, but kind of away from the center, so it's not too close. So let's call this TJ. All right. And of course, this forms an angle, right? Because it says prove that the angle between a tangent and a chord, drawn from that point of tangency, is going to be equal to 1/2 the angle between the radii to the ends of the chord. So I need to have radii going to the ends of the chord, so GT and GJ. Are we seeing how to read and set up the picture? Because pretty soon it's going to fall on you. Okay, I think you've had a couple opportunities already to experiment with this. Questions on setting up the picture. All right, let's get our given. And I don't know, the only important thing here is to specify that we've got circle G with ME tangent at T. I mean, everything else is really painfully obvious that GT and GJ are radii, that TJ is a chord, so you'll just leave it there. Circle G with ME tangent at T. And what was it we wanted to prove again, Genesis?
Then the angle between a tangent and a chord drawn from the point of tangency are equal to 1/2 the angle between the radii to the end of the chord.
All right, so the angle between the chord and the tangent, let's call this angle, we call it JTE, I suppose, or we could just number it
1.
1. We want to prove that angle 1 is equal to, what was it again, Genesis? Prove the angle drawn between a tangent and a chord is equal to
1/2 the angle between the radii.
Which would be what angle?
G.
Angle G. So we want to prove that 1 is half of G. Once you have that down, 2 columns, statements, reasons. Now again, if you will allow that bulletin board over there to be clanged for you, you see it, you clang it. It might help you a little bit here. Because after all, I'm trying to prove something about angle 1. I'm trying to prove something about angle G. What do I already know has to be true about angle 1? Kendall? What arc?
TJ.
Okay, we already know that angle 1, which is something I'm trying to prove something about, but will eventually, is equal to half of arc TJ. Because, Kendall, it's not a really super fast way to say it, but
Angle 4 by tangent and 4 equals half the arc.
good. Angle formed by tangent and chord equals half its intercepted arc, or we'll just say half its arc. All right, we're also trying to prove something about angle G. What am I trying to, well, what do I already know about angle G? Audrey? Okay, angle G, because it's formed by radii, is a central angle, so therefore we know that. All right, so number 3, we could say that, what was it again?
Angle G equals arc TJ.
So again, it's kind of picture clang, if you will. There wasn't really anything specified out here per se. Well, actually, there was a clang in the given that we would normally address here. Anyone see what the clang would be normally? Oh, well, let me stay focused here. Audrey, reason.
Angle formed by 2 radii equals arc.
Or you could say a central angle is equal to its arc. There is a clang that I normally would have gotten right. Tangent. What's normally my clang for tangent, class? Perpendicular, right? So normally I'd say clang. Chris?
Perpendicular.
What?
ME is perpendicular to TG.
Yeah. Yeah. GT and ME are perpendicular.
We already know.
Normally I would get that. But I kind of already knew where the proof was going, so I skipped that
We
clang by
also
accident.
already know angle 1 is half of angle G.
What do you mean?
Because angle 1 equals half of angle TG and angle G.
Not angle TG?
Or arc TG.
TJ.
And angle G equals a full arc TJ.
So we could literally substitute G in for the arc, couldn't we? And angle 1 equals half of angle G. So yeah, we didn't end up needing the whole perpendicular thing, but normally a tangent proof, right? Good to remember that clang perpendicular. But yeah, by a simple substitution, we're able to get this proof in short order. Questions on this? Questions on this? All right, your homework this evening is to do page 157. Page 157. Exercise 3.19b. You're going to do number 2. That's the middle section, number 2. All right, there are 2 number 2s on the page. We want exercise 3.19b, number 2. All right? Also a test coming up on Wednesday. Test coming up on Wednesday. So,
Can you say it one more time?
page 157, exercise 3.19b, number 2.
We're done early.
All right. Once you get that down, you are once the bell rings, you are dismissed and have a wonderful weekend.